All right, so today we're going to be talking about infinite series. But first, we got to start with the concept of a finite sum. And we've done a few of those before in calculus. So, for example, if you have the sum of I equals 1 to n of I, and now the triangular numbers, remember we had this kind of formula, we had a closed form for it. And but more generally, you could have things of the form I equals 1 to n of some ace of I. So now you have a sequence of coefficients that you're going to be adding. So ace of 1, so ace of 2, and I continue to add like that all the way to ace of n. And we have looked at these types of sums, and I have a video on the channel for those kinds of sums whenever they're finite. And I'm going to put a link in the description below so you can just follow quickly and watch it um, if you haven't done so. So the idea here is we would like to make sense of things that have infinitely many terms. And when we did integration, remember we did things like limit as n goes to infinity of these kinds of things. So now we're going to formalize this idea. The reason why we could take a limit before was because we were able to write it as a closed form. So we had a function that we were able to convert this into. And now we just dealt with this limit as the limit of a function. However, now we're going to think about these kinds of sums, but where we don't necessarily have a closed form for the partial sum, for the sum to n. So taking a limit just in the sense of a function doesn't quite make sense. So let's to do that, then think about a what will a series be. So I'm gonna write the definition, and we will firstly want to do a formal series. So a formal infinite series. And that's going to be something of the form sum from I equals 1 to infinity of a sub I. That's going to be called a formal infinite series because we're just going to define this as an object. And we're not going to care whether this is a number, if this adds up to something or not. We're just going to write it algebraically. So this the question will be, when can this sum add up to something? Because, for example, if I were to add I equals 1 to infinity of just I, you'd be adding 1 plus 2 plus 3 plus, and despite what some people may tell you, this is going to be marching out to infinity. So a formal infinite series will allow me to write anything, regardless of whether it converges or if it becomes infinite or whatever. So the for a convergence, so we say that a formal infinite series converges if and only if the following happens. The sequence Sn from n equals 1 to infinity converges where Sn represents the sum from I equals 1 to n. So just n many terms. And by the way, the infinite power series, I should have called this one, what do we call it? S? That's the one I was referring to. So the infinite power series S, this one right here, converges if the sequence of the partial sums converges. So what does that mean? So what does it look like? So for example, for our silly example that we had, when I is equal to 1 to infinity of I. So what would we need for this to converge? Well, we would need that the sequence of the partial sums, so the sequence of 1, 1 plus 2, 1 plus 2 plus 3, all the way out to infinity, that should converge. But now we do have a formula for the nth term of this sequence. The sequence, these are the triangular numbers, right? So you're adding 1, 1 plus 2 is 3, 1 plus 2 plus 3 is 6, and all these numbers are of the form n times n plus 1 over 2. You saw those when we started doing integration by definition. So from n equals 1 to infinity, this is our sequence of partial sums. Now, you can take a limit of this sequence because we have a closed form. We can take a look at the limit, and the limit itself is going to go out to infinity. Limit as n goes to infinity of this goes to infinity. So I should add something to my definition. If the series does not converge, we say the series diverges. So this one right here, because the limit does not exist, we say that this diverges. All right, so let's take a look at one that actually converges. So we're gonna do a typical example of one that converges. So this is going to be the case of a telescoping series. And I'm gonna take the most basic examples. So let's say I'm gonna even write it. Let's say that we in the generic form. We're not gonna do partial fractions or anything. So we're gonna say from I equals 1 to infinity. We want to look at that. And we're going to do here, say something typical, 1 over I minus 1 over I plus 1. So what we have to do then, to see if this converges, we have to create this series of the partial sums. So we're going to start with S1, which would be the sum from I equals 1 to 1 of 1 over I minus 1 over I plus 1. So there's just one term here, and it's going to be equal to 1 over 1, 1, minus 1 over I plus 1. 1 plus 1 is 2. So it's just going to be 1 half. S2 is going to be the same thing, sum from I equals 1 to 2 now, because n is 2, of the same term, or same summand. And here I would have the first term when I is equal to 1 is going to give me the same as above, 1 minus 1 half. Plus, this is the I equals 1 term. I equals 2, I'm going to be plugging I equals 2 is 1 half here, minus, I plug 2 here, 1 over 2 plus 1, 3. So this is the case I equals 1, or the term I equals 1, I equals 2. And now we can notice that the middle term cancels. That's why it's going to be called telescoping. And it's going to end up being 1 minus a third. Just made 2/3. S3, you're going to be doing the same thing. Adding from I equals 1 to 3 of the same 1 over I minus 1 over I plus 1. So the first two terms, I equals 1, I equals 2, are the same that we had before. I'm going to write them out even though we already did the cancellation, just so we see how things work. And then the third term, when I is equal to 3, 1 over 3 minus 1 over 3 plus 1 minus 1/4. And you'll see that the middle terms are going to cancel. 1 half with negative 1 half with positive 1 half, negative 1/3 with 1/3, and that's going to be 1 minus 1/4, which is 3/4. So it seems like all the terms are going to cancel, and you're going to have 1 minus 1 over n, which is going to be n minus 1 over n when you do a common denominator. And if you test your hypothesis here with n equals to, for example, um, well, fail, massive fail. This n is not going to be n, it's going to be n plus 1. Oh my goodness. So plus 1 minus 1 just goes away. So if you test your hypothesis now, you see, thank goodness I said that. For n equals to 3, you get 3 over 4, which is what we got. For 2, 2 over 2 plus 1, 3, 2/3. And for 1, you get 1 over 2. And this is not a proof you'd have to do a proof by mathematical induction to be perfectly precise, but this suffices for us because we know that in this telescoping series, things are going to cancel in between. So now the sequence that you're interested in is looking at the sequence of the partial sums from n equals 1 to infinity. And this sequence is nothing but the sequence, in this case, I have a formula for it. The sequence of the n over n plus 1 as n goes from 1 to infinity. So the limit of this sequence, you see, sequence of partial sums, I'm using a sequence to compute the limit or the value of the series. So I'm using the sequence of the partial sums to compute what will be the series, which is going to be I equals 1 to infinity of, in this case, 1 over I minus 1 over I plus 1. And this limit here, I just wrote this as a to tell you what I'm obtaining when I do that limit, is going to be the limit as n goes to infinity of n over n plus 1, because that's going to be the limit of the function that determines each of the nth terms. And this is just a rational function on n that has the same degree in the numerator than denominator. So you do the ratio of the coefficients and you just get that this is 1. Also, you could have taken the limit from this expression and you'd have seen that this goes to 1. All right, so that tells us that this sum from I equals 1 to infinity of this telescoping term, 1 over I minus 1 over I plus 1, converges, and it converges to the value of 1. So we have already the example of one series that converges and one that diverges. And in this both cases were rather nice because I actually had a formula for the nth term of the partial of the series of the sequence, sorry, of partial sums of so in this case I was able to find a rule or a closed form for each of the terms. So this should have been a capital N, probably. I hope that was not confusing. And if the limit, we could see it would diverge, or it would go to infinity, and in this case, this limit actually stayed at 1. So we have two examples there. Now, we're not going to be as fortunate, so don't get under the impression that we're going to always have a rule and just take a limit and be done for the partial sums or um, the truncated sum. So we're not going to be as lucky. So what we're going to be doing is we're going to have to come up with a lot of different rules to determine whether a series converges or not. And it's very, very seldom the case that we're actually going to be able to give the value of the sum. Often this is just going to be a numerical approximation, but we need to know whether it converges or it diverges to even know if our approximation makes sense or not. So one last type of series, which is called the geometric series. Let's talk about that and then we leave the limit at that to limit the video. So in this case, we have things of the form I equals 0 to infinity. That's the idea of that. Of things of the form r to the I. All right, so these are going to be things like of the form 1 plus r plus r squared plus dot 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 all the way out to infinity. So we want to analyze this little series or this series and find out what's going to happen. So I want to remind you of what happens in the finite case. So I'm going to look at Sn for this particular infinite series. So if I truncate it at n and look at what happens here, starting at I equals 0, not 1, to n of Ri, that's just going to be my sum of 1 plus R plus dot 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 all the way to R to the n. And this is one that you have seen these types of expressions, even though right now you don't think so. But for example, when you did the difference of cubes, you had something like 1 minus r cubed was going to be 1 minus r times 1 plus r squared. You see, this term right here is just the same as what you have here, except it's stopping at 2 and n equals to 2. So based on this, I'm going to go ahead and of course we would have to, again, by mathematical induction, establish the following formula I'm going to give you, but I'm going to try to motivate it a little bit. So if you grab 1 minus r and you multiply it times this expression we have here, 1 plus r squared plus r to the n, what you're going to have, and this is, by the way, 1 minus r multiplied times Sn. That's going to be nothing but the following. You're going to have 1 that multiplies this one, so 1, plus 1 that multiplies this one, so plus r. But I'm gonna do it in steps. I'm gonna grab this one and I'm gonna multiply it times 1, so minus r, and then I'm going to multiply this one times this one, so minus r squared. So you see, I did the first and the second times the first two. I'm going to continue. Then I'm going to go ahead and say now the first again, plus r squared, plus r cubed. I'm going to do the next two times 1, r squared, and then r cubed over here, and I wrote squared, cubed. And then I'm going to grab this r, and I'm going to multiply it times the second two. So minus r times r squared, r cubed, minus r to the fourth. The next plus would give me a plus an r to the fourth, and I'm going to continue like that until I get to the last one, where I'm going to do plus r to the n, well, dot dot dot, r to the n, and then minus r to the n plus 1 when I multiply this r to the n plus 1. So this one hitting the r to the n, and this negative r hitting the r to the n plus 1. So you see how a lot of things in the middle cancel. In fact, pretty much everybody will cancel. This will cancel with the next, and this one will cancel with the predecessor. And you're going to end up, and this is where you're going to have to believe me, if not, we have to establish this by mathematical induction, but just so you see the pattern, that's what you're gonna get. So now that I added a page here, well, the equation that we obtained was 1 minus r, and by the way, I understand that this is, you'll have to take a step of faith here to believe this formula, but I hope I gave you enough of an idea. Now the beauty of this is that you can then get a closed form for this partial sum. Now, I am, again, getting you into the habit of thinking that there is always a partial sum, and it's not. That's why we're exploring this very special series at the beginning. And then soon enough, I'll tell you, well, you know what? Those are about it. We know the sums are very, very few if you consider how many you could cook up. In any case, now we have a sequence of partial sums. In fact, you can start this one at 0 because I starts at 0, and it's gonna be just the sequence of 1 minus r to the n plus 1 over 1 minus r, where n starts at 0 and goes to infinity. Now, this is an interesting one because you're gonna have to do the limit now. So my geometric series, let's write it like this: I equals 0 to infinity of r to the I is going to be the limit as capital N goes to infinity of this 1 minus r to the n plus 1 over 1 minus r. And now this is very interesting because it all hinges on this term. This is the only thing that depends on n. You see, you can have the 1 over 1 minus r, if you distribute that, that doesn't depend on n minus the limit. In fact, yeah, let's do this. Limit as n goes to infinity of r to the n plus 1 all over 1 minus r. So you see, all hinges on where this thing is going. This limit is what tells us everything. As it turns out, that limit as n goes to infinity of r to the n plus 1 will depend very much on what the value of r is, the absolute value of r. So it can be either 0 or it can be infinite. Um, Now, I want to not consider the case when r is the absolute value of r is equal to 1, because there I have to do a very different analysis there, because you'll be adding either an alternating a series. I haven't introduced an alternating series, but a series that has one and negative ones added and in an alternating fashion, or you would have just one, 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 and added together. I think that the latter one is pretty simple to say, or pretty easy to say that it diverges. But when you have negative one and one, that is a little bit more interesting, and that all connects to something called Cesaro sums. So that those cases we're gonna leave alone. I'm gonna just consider the case when r is either. Another thing, r being negative would also be extremely a lot wilder to take care of. We're not going to do that. I'm going to consider r positives, and I'm going to look at the case when r is between 0 and 1. Absolute value of r, sorry. Actually, take it back. I said the negative ones is difficult. In fact, that's not the case. I lied to you. So we're gonna do the case. In fact, whenever it's 0, you also get 0. There's no distinct, no difficulty there. And here, when r is strictly greater than 1, you get that that goes out to infinity. So the series, the geometric series, is going to diverge in this case, and it's going to actually converge between when the absolute value is between 0 and 1, including 0. So that's what we're going to write here. So the sum from I equals 0 to infinity of r to the I is going to be equal to 1 over 1 minus r. So only this term would survive if the absolute value of r is between 0 and 1. All right, so that's another case where we can actually determine the sum, and of course diverges otherwise. But this is one we're going to be using, so I do want to keep this one. And this video turned out to be quite more theoretical than usual, but I think that's just what is needed. So we'll wrap it up here, and I hope that this all makes sense. If it doesn't make sense, please let me know in the comments below, and if it warrants more explanation or anything, I'll just create another video as soon as possible. All right, guys. Thank you for watching, and I'll see you in the next video.